When it starts, so you are already clicked, it seems.
Okay.
You can stop that actually.
Okay. Yeah. So, good morning, everyone. This is the fourth and final day of Career Days 2024. And today is the fourth day, that is called PTMT Day, dedicated to PTMT alumni. And we are very fortunate to have Dr. Surinder Singh Kainth among us. So, he will be delivering the lecture, Navigating the Axiom of Choice. So, first, let me introduce the speaker. Dr. Singh, he is an associate professor in the Department of Mathematics, Panjab University, Chandigarh. He did his PhD from IIT Bombay in 2012 under Professor I.K. Rana. His research interest is integration theory as well as graph theory, although they look different, but he is interested in both. Uh, Dr. Singh has published many research papers in various reputed journals. And it is very noteworthy to say that he has authored a comprehensive textbook on metric spaces also. This is the book from the Springer, and this is a very nice book. I have gone through it. There are many things that is not there in many of the books. Not only that, he has delivered many invited talks. Not only that, he is recipient of many prestigious prizes and scholarships throughout his life. And he is very much enthusiastic in writing scientific articles in Punjabi, in mainstream Punjabi newspapers also. And last but not the least, he is a poet too. So now I feel privileged to invite Dr. Singh to deliver his talk. So welcome, sir. Now the screen is all yours.
Thank you, sir. Thank you, Uday Shankar ji. I'm really delighted to be a part of your club and to present this talk here. And thanks to you as well as all the organizers of MTTS. So the topic of this talk is navigating the axiom of choice. Uh, Axiom of choice is something which is present in many results, many proofs that we come across in diverse branches that it is being used. Easily navigate it and avoid its usage by some routine argumentation. In some situation, it is not that easily possible. I will be discussing all that. So this is the outline of my talk. I will start with the basic motivation of the act of choice. And then we will see some ideas that the axiom of choice can lead to disasters. Its negation also leads to disasters. And then some proofs which use axiom of choice, they can be modified to proofs which are independent of this axiom. And sometimes a completely different ZF proof is required to make it independent of choice axiom. And so I will discuss all this and along with some equivalents of axiom of choice, which are, of course, which cannot be proved without axiom of choice, like the Tignoff's theorem and some other results which use axiom of choice and which are in fact equivalent to axiom of choice. So let me start with this well-ordering theorem. So if X is a non-empty set and you have a relation on X, we call the relation to be a well-ordering if it is connected. Means for all X, Y, Z in X, such that X is less than, it is transitive, it is connected, and every non-empty subset of X has a least element. In other words, you pick up any three elements such that X, Y, Z, such that X is less than Y and Y is less than Z, then you have X less than Z, means transitivity. And if you have any 2 points of X, then either one is less than the other or both are same. And third, that any non-empty subset of X has its least element. So, so if you have such a relation, it is called a well ordering. So I intentionally denoted this well ordering with this notation for strict order, so that this last statement makes sense easily. So anyway, so these are some examples. The set of natural numbers is a well ordered set because you pick up any non-empty subset of it, it has its least element. Its infimum, its minimum lies in that set itself. The set of positive reals is not well ordered. Why? Because of many reasons. The set itself has does not has any least element, right? And you consider the open interval 0 to 1, that does not has its least element within itself. So similarly, the set of integers is not well ordered. So this is well ordering. So although I have used the notation for strict order, but it could be any relation. Okay. Now, the well ordering theorem by Zermelo that appeared in 1904 says that every non-empty set has a well ordering. In other words, given any non-empty set X, there exists an order on that set, which is a well order. So now let us see where does it lead us to? So by the well ordering theorem, I will abbreviate that as WAT. So by this WAT, suppose so let this symbol strict less than symbol denote a well ordering on the set of reals. Set of reals under this order has its, because it's a well ordering, and you let x naught denote the minimum of the set of reals with respect to this order, and then let x1 denote the minimum of the set of reals minus x naught. So this set of reals minus x naught is a non-empty subset of reals, so it will have its minimum element. So we denote it by x1, and then we note that this x naught is less than x1 because x naught was minimum of all reals and x1 is minimum of a subset of reals, proper subset of reals, which does not include x naught. So therefore, there is no real number x that lies strictly between x naught and x1. So that is a serious issue. Like you have an order on the set of reals for which you have a minimum element and the next element, and there is no other element in between. And then if n is a natural number and suppose x naught, x1 and xn minus 1 have already been chosen, and then we consider x naught, xn to denote minimum of reals minus all the previous xi's, x1, x2, xn minus 1. And so by induction, we have a strictly increasing sequence xn of real numbers under this order, such that there exists no real strictly between any two consecutive terms of this sequence. After that, as we know, the set of real numbers is uncountable. Let R1 denote the set of real numbers minus this whole sequence. The sequence starts with x naught. So, and then see, reals are uncountable. Removing a countable set from reals still keeps it a non-empty set. So R1 is a non-empty set. And let x omega denote minimum of R1, which exists because the order is a well ordering on reals. So again, under the same order, you consider minimum of R1 minus x omega, and you denote that by x omega plus 1. And you just continue this, and as earlier, you just denote x omega plus n as the minimum of R1 minus those finitely many x omega plus 1 and x omega plus n minus 1, all these finitely many numbers. So continuing like this, we obtain countably many sequences of the form x naught, x1, x omega plus 1, x2 omega plus 1, and so on. And there are, you pick up any two consecutive reals in this sequence, there are no reals, not even single real between these, between those two terms of any such sequence. And this leads to a lot of paradoxes related to the cardinality, the ordinals, and this led to a lot of serious mathematics. And when this, all this is due to the well-ordering theorem. And when this well-ordering theorem appeared, it led to a lot of controversy, and therefore, mathematicians, they paid attention to it, and it was realized that this assumes a result, the axiom of choice. What is axiom of choice? I write that as AC. AC is basically that if you pick up any non-empty collection of non-empty sets, then there exists a set which is contained in the union of those sets and contains at least one element from each of those sets. So if X alpha denote that family of sets, then there is a set C, so that C intersection X alpha contains at least one element for each alpha. So this is being used in the well-ordering theorem. And in other words, for every non-empty collection X alpha, Cartesian product of X alphas is non-empty. So, when it appeared that the well-ordering theorem assumes axiom of choice, then it was natural to question this, but it appears so simple that it is really, it appears like a paradox, the well-ordering theorem. And as I said, well-ordering theorem leads to a paradox about ordinals and cardinals. So this axiom of choice appeared as a base to this, as an assumption to the proof of well-ordering theorem. And then mathematicians, they collected the results. A lot of basic results were using this axiom of choice. Then if you question well-ordering theorem, then all those results have to be questioned. So this opened a Pandora box in mathematics, in set theory particularly. And I will be discussing some of glimpse of that. Okay, here in the standard axiom of choice, so there X alpha is any collection. It could be a countable collection, it could be an uncountable collection. But many of the important results of analysis and algebra, they use countable version of this axiom of choice. So that is called axiom of countable choice. Okay, so the disasters with axiom of choice. So if you assume axiom of choice, then the unit interval can be written as the disjoint union of two sets. So not only the well-ordering principle is a disastrous result, appears to be a disastrous result with axiom of choice, but many others, like, so not only this, like the unit interval can be written as a disjoint union of uncountably many sets, each having Lebesgue outer measure 1. If small c denote the cardinality of reals, then the unit interval can be written as a disjoint union of C many sets also, each having Lebesgue outer measure 1. So, and if you assume the negation of axiom of choice, so then again you have some serious consequences. Okay. So once this axiom of choice was formulated, it was immediately realized that it had been widely used in mathematical reasoning, even although some mathematicians who rejected it, they use some explicit version in their results. Okay. So these are some results which are not true if the axiom of choice is false. These are in fact equivalent to the axiom of choice. The first one is that every vector space has a basis. Then every product of compact topological spaces is compact. This is the Tikhonov's theorem. And given any two non-empty sets, there is an injective map from one to other. Or in other words, given any two non-empty sets, the cardinality of one among them is less than or equal to the cardinality of the other. And there are many other results. These are some important set theoretic results like Zorn's lemma and Hausdorff maximality principles. These are also very fundamental ideas to prove many other results in diverse branches of mathematics. Zorn's lemma says that every partially ordered set has a maximum chain. Hausdorff maximality principle says that every chain has an upper bound, then X has a maximal element. So these are also equivalent to the axiom of choice along with the well-ordering theorem. So these are some quotes about the axiom of choice. From an infinite number of pairs of socks, the axiom of choice is necessary to select a set having one from each pair. Because these are not distinguishable. The socks are not distinguishable, but shoes are distinguishable. That's why the Russell said that for socks, you require axiom of choice. But however, the same is not true if we have a pair of shoes instead of socks. So, and here it should be noted that the number of pairs are infinite. So Jerry Bona said the axiom of choice is obviously true. The well-ordering principle is obviously false. And who can tell about the Zorn's lemma? Okay, one thing to notice is that any proof which use axiom of choice, it establishes only the existence of the required objects. And therefore, these proofs are existential, not and non-constructive. Like the proofs of this, every vector space has a basis or unit interval is a disjoint union of sets each having outer measure 1. So constructive proof means which gives you the object explicitly, but axiom of choice leads to non-constructive proofs. However, a non-constructive proof may not always depend upon axiom of choice. So I'm giving a few examples here. There are rational numbers a and b, so that a power b is a rational. There are irrationals a and b, so that a power b is a rational number. So first, let me discuss a non-constructive proof. Let x denote square root 2 power square root 2. And if x is a rational number, then we take a to be square root 2 and b to be the square root of 2, and we are done. And if x is not a rational number, therefore x is irrational. So take a to be x square root 2 power square root 2 and b to denote square root of 2. And then a power b is 2, which is a rational number. So in this proof, we are not sure whether this root 2 power root 2 is irrational or not. In the result, we required two irrationals, a and b, so that a power b is irrational. We have simply established that there are such numbers. But what are those numbers? This proof does not explicitly give you those two numbers. So now, next I am providing a constructive proof. Let a denote square root of 2 and b denote log of 9 with base 2. And then a power b is 3, okay, which is very obvious, which is a rational number. And the square root of 2 is an irrational number. So that's a high school exercise. And again, with a little basic analysis, basic reasoning, you can show that this log of 9 with base 2 is not a rational number. So if it is a rational number, then it is some m by n for some integers n, and this implies that 2 power m is 9 power. Yeah, so here is a typo. Okay, So 9, so 2 power log of 2 with log of 9 with base 2 is equal to 2 power m by n. Therefore, 2 power m is equal to 9 power n. So it should be 9 power n here. And that is impossible because this left-hand side is always odd and right-hand side is even. That's not possible. So in this section, given irrationals a and b, for which a power b is a rational number. So it's a constructive proof. So, but axiom of choice always gives you a non-constructive proof. So that's one serious issue with the choice axiom. Okay, so here is another example that square root of 2 plus square root of 3 is an algebraic number. Algebraic numbers are those numbers which are roots of polynomials over integers. And this number is algebraic. To prove it, you first show that the set of algebraic numbers, they form a field, and then that proof is so after that you just show that root 2 plus root 3 is is an algebraic number because that set is a field. Or otherwise you simply find an explicit polynomial satisfying this number root 2 plus root 3. So this is the difference. Anyway, let me come back to the theory. Basically, basics of axiomatic set theory. So I will quickly review this. Most of these are well known. The language of set theory. So whatever in mathematics we discuss, all that is a set theory, I would say, because our objects are either sets or functions or equations. Equations are basically, they can be expressed in terms of functions, and functions can be expressed in terms of relations. Relations are sets. So everything is a set theory, I would say. So there is a naive set theory and an axiomatic set theory. So in set theory, we have these are the objects which we often use. The names for sets and the members of sets and the membership symbol, equality symbol, negation symbol. Then the logical connectives, quantifier symbols for all, there exist brackets, some other types of brackets to distinguish objects. And any combination of these is known as a formula in the language of set theory. So this LAST last is an abbreviation from the Devlin's book, Joy of Sets. So I really appreciate this category. There are a certain set of axioms which have been almost unanimously assumed to be a standard set of axioms for our modern mathematics. The first is that there is a set having no element. We denote that by phi, null set or empty set. Then if X is a set, then there is a set containing all and only subsets of X. We denote that by P of X, and we call that as a power set. And the axiom of infinity, there is a set which contains empty set and singleton set. Yeah, there is a set which contains empty set and singleton set X whenever X belongs to X. So it means it contains a singleton set containing phi, and then it contains singleton set containing the singleton set phi, and so on. So there are infinite number of elements in it by this particular assumption. If X is a set, then there is a set consisting of all elements of X. And then axiom of X extensionality. I won't be, I think I should quickly pass these because discussing these will lead to a lot of time, and we won't be explicitly using any of these axioms. So axiom of subset these are some standard set of axioms known as ZF axioms, and these provide a base for our set theory and modern mathematics. And along with this, the choice axiom or the axiom of choice, that is that is called ZFC. It is called ZF set of axioms. Okay, so here, so even our set of, let me explain a bit about these axioms, a little consequence. Although the set of non-negative integers can be given very nicely by Pino axioms, but these ZF axioms also lead to the set of positive integers. So you consider Z. So let's consider a set containing empty set, set containing empty set, set containing empty set, and empty set, and so on. And then the first element phi is denoted by 0, set containing 0 is 1, and so on. Set containing 1, 2, and minus 1 is n. And therefore, this way you have all non-negative integers, and for each x in this set, you define x plus 1 to denote minus 1 till x. So that way you have the set of non-negative integers, and for any n and m in this set, either n is a subset of m or m is a subset of n. And if n is a subset of m, you call n to be strictly less than n is less than or equal to m, and otherwise m is less than or equal to n. And then you just define addition, multiplication also using these orders. So ZF axioms lead to this, and then even the well-ordering principle for natural numbers can be deduced from it. So in my book, I have worked out this in detail. Okay, so several standard proofs of the basic results, they use the axiom of choice without explicitly mentioning it. Shortly, we will be coming to those proofs. The proofs using ZF axioms along with the axiom of choice are known as ZFC proofs. And the other ones are not, which are independent of this axiom, are known as ZF proofs or choice-free proofs. And most of the time, the ZFC proofs are cases where drastically different cases, the use of axiom of choice cannot be avoided. So now let me come to one standard proof that the unit interval is a compact set. Suppose not. So if this unit interval is not compact, then there is an open cover omega of this unit interval having no finite subcover. And then what we do, we just divide the unit interval into two pieces. Wait a minute, let me use yeah. Okay, so the idea is this. Okay, anyway, suppose yeah, I wanted a straight line. Yeah, suppose this line denote the unit interval plotted on the real line. And this is my 0, this is 1. If this is not compact, then there is an open cover omega of this interval having no finite subcover. Okay, after that, what we do, we subdivide it into two parts, two intervals, 0 to half and half to 1. And then either this first interval 0 to half has no finite subcover, or half to 1, this subinterval has no finite subcover. Because if both of these have finite subcovers out of omega, then the union of those finite subcovers is again a finite subcover of the unit interval, which is these has no finite subcover. So we choose one of these. Suppose this one has no finite subcover. We focus on this, and then we just do the same to this first interval. We divide it into two equal portions, equal subintervals. And then each of one of these, this one or this one of these intervals has no finite subcover. So we choose one among them. Suppose this subinterval has no finite subcover. Okay. And then, so this, just like this, I continue. Let me read out the slide. So let I1 denote the unit interval. We just write A1, B1 for it, and C1 denote the midpoint of the interval, A1 plus B1 by 2. And since this whole interval A1, B1 has no finite subcover, either AC1 or CB1 has no finite subcover. And let I2 denote the interval, one of those intervals which has no finite subcover. And suppose this one. And then you just okay, then you do the same to this I2. Okay. And yeah. So write A2, B2, let A2, B2 denote I2, and you similarly, you just, if this is your I2, okay, and then you just take it, divide it into two finite subcover, and then again divide the rest next one into subintervals, and you do the same. So inducting like this, you have a nested decreasing sequence of closed bounded intervals in such that no in has a finite subcover from omega. And let I and length of in is 1 by 2 power n minus 1, which tends to 0. And then by nested interval property, intersection of INs is a singleton, is a singleton x. So, and for some x in the unit interval. And since x is in the unit interval, there is some open set O containing x. And since O is an open set, there is a delta positive, so that interval with radius delta centered at x is contained in O. And as length of these intervals tend to 0, there is some capital N, so that length of in is less than delta, and therefore this in is a subset of x minus delta to x plus delta, which in turn is contained in O. Becomes, but that is not true, because you have chosen in to be an interval which has no finite subcover from omega. Then how can a single set O contain in? So that's a contradiction. So this is the standard proof for that the unit interval is compact. So this basic real analysis proof uses axiom of choice, because every time we are bisecting the interval, and then out of those two intervals, one of the intervals, at least one of the intervals has no finite subcover, and we are choosing that. So that choice of interval at each stage, basically that uses axiom of choice, because it's an infinite process. And since it is a countable process, so we have a sequence of intervals. So here we are using axiom of countable choice, CC. So this depends upon choice axiom. Now, this can be made independent of choice axiom. Let me erase it first. Okay, so one more thing, whenever I use this word choose, axiom of choice is being used, and the proof is choice dependent. Okay. Yeah. So now I'm with a little change in the previous proof, I'm making it independent of the choice axiom. So I'm just producing the same proof with a little modification. So either AC1 or CB1, C1, either A1 C1 or C1 B1 has no finite subcover. Okay. So we at every stage we had two intervals. We bisected our available interval which had no finite subcover, and then bisecting it, we got two further subintervals of equal length, and then we claimed that one of them has no finite subcover, and we choose one. But instead of that, if you select the left interval first, in case it has no finite subcover, and if it has a finite subcover, then you choose the right subinterval. So with this rule, you are avoiding the axiom of choice. And then your rest of the proof is same, not an issue. So only where you had used the choice axiom, so you simply need to observe that and suggest some rule to avoid the choice. So here, let me discuss one other example. The Bolzano-Weierstrass theorem that every compact subset of reals, if X is a compact subset of reals, then every infinite subset of X has a limit point in X. Suppose not, and let E be an infinite subset of X having no limit point. Then for every X in for every having no limit point in X, yeah. Then for every X in the main set X, capital X, one can choose an open interval Ix containing X such that Ix contains at most one element of E, namely X. And that is Ix intersection E is a subset of X. So this is basically the definition of point. Okay, and then where X is in capital X is an open cover of X. Since X is compact, there are X1, X2, Xn such that X is contained in union of these intervals, finitely many intervals. And therefore, E, which is E intersection X, because E is a subset of X, it is contained in union of E intersection IXI, because X is contained. And this E intersection Xi is a subset of singleton Xi. So this union is a subset of this finite set X1, X2, Xn. So E is a subset of a finite set. So E is finite. That's not the case. E is infinite. So this contradiction ensures that every infinite subset of a compact set has a limit point. So now here this proof, very simple proof, this uses the choice axiom, because for every X we are choosing an open interval. So this choice is there. So this is choice dependent proof or ZFC proof. So now this is now I'm producing the same thing but with a little change. Let omega denote the collection of all open intervals I such that I intersection E is at most a singleton set. So you don't restrict yourself to one such open interval. So earlier you had taken one open interval. We choose an open interval Ix satisfying this property. And then I'm saying that you just consider all the open intervals having this property. Doesn't matter what. So then consider omega to be the collection of all open intervals satisfying that property. Then omega is an open cover. And the proof becomes choice-free or ZF proof. So there are many other results where a little modification to the proof gives you a proof independent of the choice axiom. So I had written the proof for uniform continuity theorem also. I am avoiding this due to lack of time. So here also, you just need to choose a particular, make it choice free. This proof is available in my book on metric spaces. Interested readers can take a look from there. Okay, so now I'm sharing a proof where you need a completely different proof to make it independent of choice. So if f is a function such that for every x naught in reals, if xn tends to x naught, then f of xn tends to f of x naught, then f is continuous on reals. So this is called sequential continuity or sequential approach to continuity. So its ZFC proof is very short and simple. It is available in all textbooks of real analysis. Suppose f is not continuous at some point c, then there is some epsilon positive such that for all delta positive, mod of f of x minus f of c is less than epsilon whenever x lies in a deleted delta neighborhood of c. And in particular, for each n, you take delta n to be 1 by n, and then you choose xn so that xn minus c in mod is less than 1 by n, while mod of f of xn minus f of c is bigger than or equal to epsilon. So when we are saying that this assertion is not satisfied, so for each delta, there is some x which violate this assertion. X for particular delta n's 1 by n. And then I get that my sequence f of xn cannot converge to c because this is always the case. Mod of f of xn minus f of c is always bigger than or equal to epsilon. But on the other hand, xn minus c in mod is less than 1 by n, so xn converges to c. So this contradicts the hypothesis. Now I'm producing the case of a proof which is independent of this choice axiom. So here I have chosen one particular xn. So this was here the choice was used, the axiom of choice. So let me discuss the independent proof. Let Rn denote an enumeration of the set of rational numbers. For every x, every real number x, let f subscript x denote the restriction of f to q union x. And then we claim that this fx is continuous at x for every x. Suppose not. Suppose at some x, f of x is not continuous. F subscript x is not continuous. Then there is some epsilon positive by n to x plus 1 by n intersection q subscript x yn minus f subscript x of x is bigger than or equal to epsilon. So by definition of continuity. And then for each n, we take yn to denote rkn, where kn is the index of the rationals to be the minimum of m, so that mod of fx rm minus fx of x is bigger than or equal to epsilon, and rm is in the closed interval x minus 1 by n to x plus 1 by n intersection rationals. So we know that there is some yn satisfying this. Okay, so we just take minimum of the index of those rational numbers as per this enumeration. Enumeration is fixed in the beginning. And since every subset of natural numbers has the smallest element, so this choice of yn basically is independent of axiom of choice. And we note that yn tends to x, while f of yn does not tend to f of x because of this condition. And now this establishes our claim. The claim was fx is continuous at x for every x. I'm repeating it. So therefore, each fx is continuous at x. And now you fix up any real number x and eta positive. Then there is some delta positive, so that mod of f of y minus f of x is less than eta by 2 for all y in x minus delta to x plus delta intersection q. Let z be in the interval x minus delta to x plus delta. And since fz is continuous at z, mod of f of z minus f of w is less than eta by 2 for some w in x minus delta to x plus delta intersection q. And therefore, mod of f of x minus f minus mod of f of x minus f of w plus f of w minus f of z. You apply the above two inequalities and this is less than eta. And this ensures that f is continuous at x. So x was arbitrary, so function is continuous. So sequential continuity implies continuity on the whole set of reals. So this proof is taken Harnick, Axiom of Choice. It's a wonderful book. There are a lot of results. There is almost everything which is on Axiom of Choice. So anything related to Axiom of Choice is available in this book. So that result was basically for all reals. Let me repeat the result. Yeah. So it is not sequential continuity at a point. The function is defined on the set of reals. We are saying that the function is continuous on the set of reals if and only if it is sequentially continuous at every real number. Now, what a natural question is that result for each point also independent of the choice axiom? So answer is that it is not true. In ZF without CC, the following pointwise analog of this result is false, that if f is sequentially continuous at x naught, then f is continuous at x naught. This is not true. This is in fact equivalent to countable choice, CC, in ZF. The standard proof of this result uses CC, and this implies CC, the countable choice. It is available at page 74 of this book. Okay, so now I'm considering last the cases where axiom of choice cannot be avoided, like this well-ordering theorem and axiom of choice. These are equivalent. Okay, the necessity holds by the well-ordering theorem that has a very non-trivial proof, but the converse is easy, very trivial. Consider, let x alpha denote a collection of non-empty collection. By well-ordering theorem, let this symbol denote a well-ordering on the union of these x alphas. Then x alpha to be, if small x alpha is minimum of this set capital X alpha for each alpha, then with these x alphas, the choice set C to be the collection of small x alphas is the required choice set. Then this C contains at least one element from each of these x alphas. So the well-ordering theorem immediately implies axiom of choice by considering a well-ordering on the union of those sets from where you need to obtain a choice set. Then the Tikhonov's theorem that the product of compact spaces is compact. So again, the axiom of choice implies that Tikhonov's theorem is a non-trivial result, and it's a very important result in topology. So I'm just avoiding that proof. I'm saying it holds by Tikhonov's theorem. The converse is very direct. Let us discuss that. Let X alpha denote any non-empty family of non-empty sets, and let infinity denote an element which is not in the union of these X alphas. And then let Y alpha denote X alpha union infinity, and T alpha denote phi singleton set infinity and Y alpha for all alpha. And then each Y alpha, T alpha, is a compact topological space. So that is obvious by the definition of this topology, and that your space is compact, X alpha is compact. And then by hypothesis, the product space Y, which is the product of each Y alphas, that is also compact. And let alpha be an index and pi alpha denote the projection map from Y to Y alpha. And then capital F alpha is pi alpha inverse of and F alpha has the finite intersection property because it's a non-empty closed subset, and the space Y is compact, so it has so every non-empty collection of closed sets has finite intersection property, which is equivalent to compactness. Yeah. So therefore, the total it has finite intersection property. And then because Y is compact, the intersection of F alphas is non-empty. And therefore, product of X alphas is intersection of F alphas, which is non-empty. So you get that Cartesian product of X alphas is non-empty, and this ensures that you have the axiom of choice. So in the beginning, when I discussed axiom of choice, I just mentioned that it is equivalent to saying that this product is non-empty. And that is obvious because then this being non-empty means there is a function from this indexing set to the union of X alphas, so that for each alpha there is some point so for each alpha, F of alpha belongs to X alpha, that is equivalent to forming a choice set as discussed earlier. Okay, so now let us discuss a few remarks. So this paper is a very fascinating paper, paradox arising from the elimination of a paradox. So in this 2019 paper, it presents the division paradox, which states that in ZF without the choice axiom, the set of real numbers can be written into disjoint classes so that there are more. So it gives it is like a tournament where the number of teams is more than the total number of players. So that kind of situation appears with the set of real numbers if you assume axiom of choice. Okay, so these are the books which are my favorite ones for set theory. The Joy of Sets by Keith Devlin and the Set Theory for Working Mathematician, published in 1992 and 1997. So Non-Measurable Sets and Functions by Koreshky, and another book by him, Set Theoretic Aspects of Real Analysis. And this is my book. All this, whatever I have discussed here, except the Tignoff's theorem and some other little results. So most of this talk is available in my book, Comprehensive Textbook on Metric Spaces. So that's all what I had to say. And these are some exercises. Yeah, so I stop here. And maybe I should discuss. Yeah, these have been already discussed, these references. Yeah. So if there are any questions or comments, that is most welcome. So, yeah.
Yeah. So thank you, Surinder ji, for your nice and very much informative talk. So I would now request the participants to please ask the speaker if they have any doubt or
Yes,
any
sir.
queries.
I have a question. Yes.
Yeah, please.
Previously you were talking that the constructive proof and non-constructive proof, right? So
Yeah.
my question is like in formal mathematics, is there any like a little tiny place for non-constructive proofs?
Could you repeat your question?
Like in formal mathematics, is there any place for non-constructive proof like compared to constructive proofs?
Is there any?
Non-constructive proofs.
No, in formal mathematics, you are not properly audible. You said
Okay, okay.
in formal mathematics, what did you say?
Is there any place for non-constructive proofs? Non-constructive proofs.
Could you please write your question in the comment?
Whatever I have understood, he asked, is there any place for non-constructive proofs? Is it all right, Sheetal?
Yes, yes, yes,
Yeah.
yes.
Is there any any text or any published book only on non-constructive and constructive proofs? Is that what you're asking?
No, not really. Actually, Sir was talking previously the point. That was my question.
So, do you want to mean that what is the significance of non-constructive proofs?
Right, right.
Yeah, I
You
think.
know,
Yeah, basically the non-constructive proof in mathematics, many a times uh, our rigorous proofs, so they just prove the existence. Like even in the applied subjects, like although this distinction I do not believe in, but anyway, in differential equations also, the existence and uniqueness, we establish it. So those are existential proofs. They don't give you explicit proofs. So many times we prove the existence of an object rather than explicitly giving the object. So it happens in all branches of mathematics, in many of the rigorous proofs, and using axiom proofs which use axiom of choice. So there, if you are getting an object, that object is not explicitly given. So that object is basically, so that proof is a non-constructive proof. If you are getting an object out of the proof, if you are establishing the existence of an object and using axiom of choice, then the proof is non-constructive proof. But my point was that the non-constructive proofs, they appear even without axiom of choice. Those two simple examples, like there are rationals A and B, so that A power B is, sorry, there are irrationals A and B, so that A power B is a rational number. So that's a very simple result. And I have given a proof which is a very one-line proof, but that is an existential proof. We do not know the exactly which one, whether root 2 by root 2 is irrational or not. But even with both of these cases, we get that there are some A and B. So we can have a non-constructive proof even without the axiom of choice. That was the point.
yes, now it's clear. Thank you.
Yeah. Any other queries? Any other queries from anyone? Okay, it seems there is no more queries. So let me again thank our speaker, Dr. Singh, for his nice talk. And we hope that in future also we'll have him for his talks.
Sure. Thank you so much. I'm really, it was my honor to deliver a talk. So I would have appreciated if there have been more questions. But anyway, thank you so much for giving me this platform to speak. Thank you.
Yeah, thank you. So I think we should conclude now. And one announcement that we have another talk, and the speaker is Dr. Monica Singh. She is here. So that talk will start from 2 p.m. So I'll request all the participants to please join at 2 p.m. So thank you. Let me stop now.
Thank you.